So I present our recent work on an MPI dialect for MLIR. This is joint work with one of my research staff members, Anton, and Jeff Hammond from NVIDIA. It comes from a research project where we wanted to take large-scale computational science applications, run them on HPC clusters, and this is a proposal of a potential new dialect for MLIR. So as you all know, MLIR works great, especially of like individual machines or cell phones or whatever you have. But obviously, there is a field in computer science, HPC, where we have large-scale systems, many nodes connected by a network. And so the question is, how can we deploy MLIR or use MLIR to deploy code on such large-scale machines? And so what I want to propose here is to kind of a step-by-step approach to pretty much add an MPI abstraction, which is the standard or well-established API for internode communication and such kind of supercomputers. So the scope and goal of this presentation is really small. So the objective really of this step-by-step approach is not that I explain you all of MPI and then when we build something large. I want to make the case that we should add something small to MLIR. In particular, we should get an MPI Hello World program running in MLIR. And so what you see here on the left-hand side is the code. So you have a message and you have a rank. And then you have a piece of MPI code. It has an init, comRank is called. And then there's an if condition to decide what kind of code should be run on each node. And let me actually go back briefly. So what we actually want to get as an output, on the first node, we want to have a message, hello there, and that should be communicated to the other node, right? And so the actual, no, come on. Again, this one, right? So this is the exact code that we want to have. The first rank 0, sends the message to the second rank, and the second rank pretty much receives the message and prints it out to the terminal, right? There's an MPI init that just says, okay, we want to set up the context of our MPI communication library. MPI comRank gives us the ID of the current node, and MPI finalize just kind of finalizes the context. Translating that to MLIR in some way is really straightforward. So what you should see here is pretty much that the syntax is different. Any one of you who worked with MLIR should recognize the percentage symbols for the variable names, but pretty much the code structure is and can remain the same. So the question really is, how can we take the MPI-specific calls and can we create a dialect around these calls, right? And so we pretty much just can go one by one. So we need MPI init. It takes 2 arguments, which in our initial proposal, we suggest to just ignore them. They are used to pass command line arguments to the MPI implementation. They are not inherently necessary. MPI comRank is just a function that gives you the current integer value of the node idea where you're running on. MPI send is something that we can, thanks to the MLIR types, we can simplify a little bit. So it just takes a message, which is a memref buffer, and then it takes 1 and 0, which is the size of that buffer or how much we want to send, as well as the kind of the rank where we want to communicate to. I didn't say that, but MPI comworld, for example, MPI is a concept of a communicator. It would be nice to model that eventually, but we can, as a kind of a default value, we can just assume that's always MPI comworld, and then in the future we can extend that MPI send operation if we really want to be able to specify the communicator. MPI receive, pretty much the same thing. I think there's a typo here. We should return actually a value. But otherwise, yeah. MPI comworld is still a constant argument that we don't know or don't want to change. MPI status ignore is, again, a special MPI feature where you can allow for status updates or status errors to be read. Often when you code generate MPI you just ignore the error message because you don't know how to handle that one. So often, yeah, you don't actually expose that in your programming model. So by default, we would also suggest to not yet expose that in the dialect. And then we MPI finalize, which again is very simple. It's just a call without any arguments. So as you see, these are only 5 operations that one needs to run on a cluster. They're quite simple. We have a PR open for LLVM, and like the MLIR project in the LLVM. And yeah, it would be nice to see if we can get that upstream. Obviously, MPI is a lot larger. So if you ever programmed on a supercomputer, you heard about maybe non-blocking sense. There's this return value handling. You can choose to have custom communicators. You have collective communication. So for example, you may want to acquire values from all nodes and accumulate them in a certain way. So there are a lot of concepts in MPI that are useful, interesting, and should eventually expand that dialect, but they, I think, are not necessary for kind of an initial dialect. The second thing that we would like to see eventually, but we don't propose at the moment, is that an MPI dialect is great. Dialects are only really useful if you can use them, for example, to lower to LLVM to actually create executable code. Again, that's something that we want to do, but I think it's also something that one can do it incrementally. But the standard approach would be, I mean, you lower all these function calls to LLVM function calls, and yeah, pretty much generate code for that. And the conclusion, so this is a minimal first draft of an MPI dialect. We plan to continue development in small incremental PRs if we get feedback from the community and actually we manage to upstream this first draft. And our long-term goal really, I think, is actually quite ambitious. I think MLIR is doing really great for single node workloads. And I think it would be nice at least to have first-class support in MLIR for HPC-style communication. And I think MPI as an abstraction is a really nice abstraction to get these kind of HPC efforts started. The abstraction that we chose in some way is very deliberately, I hope, not as controversial. MPI is a very well-established standard, which means on the semantics, I think there's very little to debate about, like, is that a useful abstraction? What exactly are the concepts that should be modeled? But that doesn't mean that there are not interesting questions in how to design this kind of dialect stack. The typical question that some of you may now ask is MPI actually the right abstraction to generate code in MLIR on these kind of clusters? And often the answer probably is maybe not, right? MPI is an interface dialect like that allows us to target these clusters, but there might be potential higher level dialects that one can build to, for example, I mean, one could have an abstraction at the tensor level to do exchange of halo exchange at the tensor level. It could be an interesting dialect that eventually could be built on top of the MPI dialect. And there are many other such dialects that I think as a community we could build and develop over time. But I think the foundation should be an interface dialect that is well established in the community that allows us to start with a common base. Yeah, that's it so far. Thank you so much.